Hey y'all. Today we're going to be discussing the mass action law. The mass action law connects directly to the equilibrium constant and is arguably the backbone of our equilibrium unit. So let's go ahead and get started. Remember back to kinetics where we used a little k? Well, in equilibrium, we're going to be using a capital K. And a big reason the capital K is utilized in equilibrium is in part because of the fact that it derives from our rate laws. So the mass action law is actually a derivation of rate laws because in the end, equilibrium is where rates of forward and reverse reactions are equal. We can actually get from a rate law to the mass action law through a couple of mathematical processes. We're not actually going to do that, but understand that the two are connected directly. In equilibrium, it's a capital K that represents our equilibrium constant. When you're writing a mass action law, the first thing to understand is that it's products over reactants. So if we're given a generalized chemical equation such as this, where little a is the coefficient for big A and little c is the coefficient for big C, what we would do when we're placing it in the mass action law is we would talk about the concentrations of those products, C and D, raised to the power of their coefficients, little c and little d, divided by the concentrations of capital A and capital B, raised to the power of their coefficients, little a and little b. This is the generalized form of our mass action law, and you are expected to know it. It's on the formula sheet, so it's not something you actually have to memorize. It is something you need to be able to actually show, though, before you do pretty much anything in equilibrium. In kinetics, one thing I told you is that we could never assume that the coefficients and the exponents were the same, unless it was an elementary step, in which case they were. In equilibrium, however, the exponents and coefficients are always equal to each other, and that's really helpful, but admittedly can be confusing if you start to mix up the kinetics reality and the equilibrium reality. The nice thing about equilibrium mass action law, again, is it's on the formula sheet. You don't have to memorize it. So as long as you have access to your formula sheet, you'll be in good shape and be able to write this mass action law all the time. One other thing to note about the mass action law is that we never include solids or liquids in our mass action laws. The reason for that is because solids and liquids have constant concentration. And as a result, they're not going to impact our equilibrium situation. So when we look at a mass action law, it's going to include every aqueous situation, every aqueous solution, or every gaseous substance, but it is not going to include solids or liquids. One other thing to keep in mind is that when your mass action law is for an equilibrium system, that means it's a system that's at equilibrium, the mass action law equals K. In this situation, your mass action law, though, is describing a system that's not necessarily at equilibrium. The mass action law equals Q, capital Q. So the capital letter Q is representing any position, whether a system's at equilibrium or not. And it's only when that Q and K are equal that your mass action law equals K. We're going to talk more about Q and K a little bit later in this unit. There are also different types of K values. For instance, our generalized K EQ with a subscript EQ just says K at equilibrium. However, there's also Kc with a subscript of C. And Kc represents concentration equilibrium, and we represent that with brackets around each of our reactants and products. There's also K sub P. This one, importantly, is for pressure or gas equilibrium. And in this case, we're dealing with the partial pressures of each reactant and product. And so the format of Kp is a little different. Instead of brackets, we're using parentheses. And instead of just putting numbers or letters to represent the compounds, we need to make sure we're representing as partial pressure, which means capital P with a subscript of the gas that we are describing. It's really important when you're writing a Kc or Kp expression that you make sure you get your formatting right. It seems a little bit minor, however, it's a big deal. It's like getting your units wrong. Right? If you're trying to express something in molarity, but then you put density, you're wrong. You just have the wrong number with the wrong unit. Same thing with when we're expressing equilibrium expressions, either Kc versus Kp. There are also other K values that we're going to deal with this year. Ksp, for example, solubility product equilibrium, Ka, or acid equilibrium, Kb, base equilibrium, and even Kw, the equilibrium of water. When we look at all these K values, those subscripts just represent explanations of what the K value is all about. It's kind of similar to when we were dealing with delta H, where we had delta H of reaction, or delta H of combustion, or delta H of fusion. All those different delta H's. The delta H concept is the same, but it gave a little more detail about what is actually happening in the process. One thing the equilibrium constant tells us is whether a reaction is going to strongly favor reactants or strongly favor products, or if it's somewhere in between. A larger K value would suggest that we have way more products than we have reactants, because again, it's products over reactants. That would suggest that our product value is large and our reactant value is small. A situation where we have an extremely large K value would suggest that the reaction has gone far to the right, or closer to completion in the forward direction. In fact, in some cases, the K value might be large enough where we do say the reaction goes to completion. That might be a K value where it's 10 to the 20th or 10 to the 30th. In some situations, the K value is in the opposite direction. It's extremely small. This means you have very few products and a whole lot of reactants. This would suggest that the fraction would be much smaller. And as a result, we would say the equilibrium lies far to the left, which means that really we would see this reaction as not going in any way, shape, or form. We actually wouldn't see any products forming, relatively speaking. So the size of the K value tells us a lot about which direction the reaction is going to favor. But one thing to be aware of is we are using these as relative assessments. And so there's not one tipping point where I say, okay, beyond this point, it goes to completion, or beyond this point, we assume the reaction doesn't happen. It's all kind of relative. And in most cases, the K value is going to be somewhere in the middle, where it's not necessarily large, not necessarily small, but instead somewhere in between. One last thing about K values is because we can't have negative concentrations or pressures, K values can never be negative. They're always positive. So when I say a small K value, what I'm really talking about would be exponents that are like 10 to the negative 20, 10 to the negative 30, all right, which means closer to zero and not getting negative, because again, K values can't be negative. All right, so go ahead and practice with me here. Here's a chemical reaction. What I want you to do is first write the Kc expression for this reaction at equilibrium, and then, because these are all gases, I want you to write the Kp expression alongside that, okay? So take a second and let's do this together. We'll do the Kc right now.
Pause!
Remember, Kc represents concentrations. Even gases can have concentrations. All concentration means is moles per liter. And so when we're looking at this, gases take up space. They have volume, and the volume is variable. So as a result, their concentrations aren't constant, and so we can use them in equilibrium expression. So what I would do is products over reactants, which means that it's going to be the concentration in brackets of NO2 times the concentration of O2. Now the NO2 would need to be raised to an exponent of 4 because its coefficient is 4, and the O2 would need to be raised to a coefficient of, or to an exponent of 1 because its coefficient is 1. We would then divide that by N2O5 in brackets raised to the power of 2 because its coefficient is 2. So this would be my Kc. Kp is largely the same, but with a little bit of difference in terms of the formatting. We need to replace those brackets with parentheses, and when we put the parentheses, we would say partial pressure as well. So it would be capital P sub NO2 raised to the 4th power times capital P sub O2 raised to the 1st power divided by capital P sub N2O5 all raised to the 2nd power. So that's how you would write a Kc and a Kp given a chemical equation like this. All right, so here's another practice problem. Let's do this one. Write the Kc for this right here.
Pause.
Well, the first thing to keep in mind is remember equilibrium constants don't include solids or liquids. And A here is a solid, so we don't include it in our expression, which means it's going to be products over reactants, which is C raised to the second power divided by B raised to the third power. And in this case, because it's a Kc, they're going to have brackets around each A and B. Or, sorry, each B and C. A is ignored because it's a solid. All right, so that wraps up today's video. Let's talk about it. Today, we looked at how to write a mass action law with both a Kc and Kp. Okay, remember the formatting is a little bit different. We also talked about how to write a mass action law, whether we're at equilibrium, where it's equal to K, or when we're not necessarily at equilibrium, when it's equal to Q. We're going to use that a little bit later in terms of analyzing whether we are in fact at equilibrium or not. All of equilibrium as a content chapter really comes back to this mass action law. You need to be able to write it, and you need to be able to solve for these variables. Most of the videos that are upcoming are going to cover exactly that. Today's video was written, directed, produced, and edited by Aista Braunfelds and Sonali Gopal. Thank you all for watching. I hope you enjoyed it, and I'll see you in the next one. P. Okay, stop it, you two.